First, I will give you the formal definition of a few terms or a few concepts. It will take time. It will take you time before you will really just get the grips of this concept. But still, we have to start sometime, and why not now? So basically, you look at the set of vectors, and this time you see I just chose this M vectors. Let me just zoom a little like this. You look at the set of vectors. It may be any set, 1, 2, 3, 5, a million of vectors, and you will call these vectors linearly or linear independent. And the formal definition goes like this. You take listen to this. It's not an easy definition, actually. Even just this statement of it, it's not so easy. There is a formal statement in the lecture notes, so you can read this as many times as you wish. You just listen right now. It says like this. If and only if, anytime you look at the expression like this, anytime you look at the, in fact, equation like this, you see, it's the thing which has my vectors, a1, a2, am, and I scaled each of them with some coefficients, lambda 1, lambda 2, lambda m. So every time you look at something like this, every time you look at something like this, if you can conclude just from one equation, if you can by some method, by some thinking, by some wild guessing, if you can conclude that this can only be true when the coefficients are 0, think about that. Obviously, when the coefficients are 0, this is 0, right? If you just plug 0 here, if you plug 0 here, if you plug 0 here, you will end up with 0. It's a triviality. But if you conclude the other way around, if you can conclude that from just having this combination 0, you can conclude that every individual coefficient is 0. If you can do that, in which case, in this case, you will call this system linear independent. It's not an easy concept, but that's the formal definition of it. I will give you some demonstrations in a second, but I just want this to sink into your head, just now. Listen to this again. Every time, if you have a system for which you can conclude that every coefficient is 0, given that the combination like this is 0, just by one single assumption like this, you conclude nothing else, just this assumption. You can conclude that every coefficient is 0. You call the system linear independent. Oops, sorry. The left-hand side of this expression, just to ease the language a little bit, the left-hand side of this expression, it has a special name. It's called linear combination. Linear combination of vectors ak. So to make the statement now, I can make this statement a little bit shorter. I can say vectors are linear independent when, from the fact that linear combination is 0, you can conclude that every individual coefficient in that linear combination is 0. Well, there is an opposite statement. Linear, I don't know, it's just, I didn't say here linearly. Well, you can judge my English anyway. The set S is said to be linear dependent, so it's the opposite. It's a logical opposite of this first definition we just discussed. We say that the system is linear dependent, where the logical opposite of this is true. Let's just see how well you observe the definition. Can you construct the logical opposite of the statement which is in front of you on display? Without just a logical opposite of it, negative. What would be the logical opposite of this implication? That the system, the linear combination like this, 0, implies that every coefficient is 0. What's the logical opposite of that? Yes, the logical opposite of that is you can find the coefficients which will make your linear combination 0, whereas not everyone in those coefficients is 0. That's the logical opposite of that, and that's the case when we call my system linear dependent. So if you can find coefficients, not everyone is 0, but the combination turns out 0, done. The system is linear, just one will do. So remember my little symbol, if there is or exist coefficients such that on one hand linear combination is 0, but on the other hand there is one, at least one will do, there is one coefficient which is non-zero. In that case, the system will be called linear dependent. Okay, like I said, don't be scared too much with this. It's a very advanced concept, You won't see much of this very abstract, I mean, in the full generality of it this semester. You will see much more next semester, but some examples, some small examples still will come up. And it's nice if you will see these examples in the general framework of this bigger general concept. But here's a few examples for you. Actually, I just made the first 3 examples which I want to discuss with you. They are here. They just try to demonstrate this concept on a simpler set of vectors when you have only 1, only 2, or only 3 vectors. So let's just look at system or set of vectors which consist of one vector A. Look at the definitions carefully, and here's a question to you. The other way around. What would be the equivalent and much simpler restatement of the linear independence and linear dependence definition in case of one vector? How would you alternatively say that the vector system of one vector, let's just look at the dependence first. Dependence. Imagine, like, let me make it simple actually. We have a system of one vector, and let's just assume that this system is linear dependent according to this definition. Okay, system of one vector which is linear dependent. That's what I mean when I say that. It's exactly here. Can you now interpret this or adjust this or simplify this for this particular setting of one vector? What it will mean for this one vector? Dependent. So yes, please. Vector A will be equal to 0. That's it. That's all there is to it. For the one vector, it's just linear dependence. It's either vector 0 or vector non-zero. I'll prove it to you. Look at this. Imagine this system. It's a big name for just one vector, a system of vectors. This system of vectors is linearly dependent. According to this, there will be coefficients such that linear combination is equal to 0, but that's all there is to the linear combination of this one vector, right? And there must be 1 between these coefficients, which is non-zero. But we only have one coefficient, isn't it? There's no any other coefficients. So my coefficient lambda is in fact non-zero. That's just direct interpretation of the second clause of this definition. Now, all I have to do, I have to multiply my equation by the inverse of lambda, which is a doable step because my lambda is non-zero. And if I multiply by the inverse, I will end up with vector A equals 0. That's why this huge, intimidating definition in case of one vector, via this little line of reasoning, converts into the simple statement vector 0 or non-zero. Because of this little line, 0 vector will always make system dependent actually. In case of one vector, that's the line which demonstrates that, you can extend this line to any set of vectors. It's easy. If you have 1, 0 vector within this combination, you can always put non-zero coefficient next to the you can always put non-zero coefficient, say 1, next to the 0 vector, and you can put zeros next to the rest of the vectors. You will end up with a linear combination which is 0, but not every coefficient is 0. So 0 vector will always ruin the system. It will always turn the 0 vector will always convert the system into the linear dependent system. Oh, well, we have 1 minute. I'm just wondering whether you can tell me what will be the manifestation of the linear dependence when we look at 2 vectors. Look at this. If I look at the linear combination like this, of 2 vectors now, right? If I look at this definition of dependence, I look at the 2 vectors and I assume that they are linear dependent. So it means I can find a linear combination which returns 0, but one of these coefficients is non-zero, one of them, either lambda or mu. Which one is irrelevant, but for the sake of demonstration, we can make the assumption which one exactly. say in my demonstration, I made the assumption that let's just say lambda is non-zero. If it is mu rather than lambda, you can do the same trick, but I mean, you can make the symmetrical adjustments and it will be the same argument. So if my lambda is non-zero, again, I can solve for a here, because having lambda non-zero, I can always multiply by the inverse of lambda. So if I solve for a, that's what I will come up with. And we all know it means that my vectors are parallel. So for the case of two vectors, linear dependence, it's a fancy, like a more general term for just being parallel.